All right. Thank you, everyone, for joining the latest Trees Around the Globe student research campaign. Today is the 11th of December, 2025. And the topic for today is the state of trees, December 2025. And this great title that our featured speaker, Dr. Erika Podest, came up with, The Rhythm of the North, Tracking the Vegetation Growing Period from Space. And I have to tell you, Erika, that, when we mentioned this, title to multiple people when I'm presenting it at different, things when people want to know what the next webinar was. Everybody loves this title, and I said I'm good at coming up with titles, but lately the guest speakers have been coming up with titles that so much better than I've come up with in the past. So people really love this title, and they loved Adriana's title in the last webinar for November. So very appreciative of these really these catchy titles. So and very concise, catchy titles, because I kind of come up with titles that are very long, which some folks that I work with don't like the really long titles. So, but thank you. So we're going to be talking about today the rhythm of the North, tracking the vegetation growing period from space. So I have a couple things I want to show you here, which are pretty cool. I'm going to end today later after all the presentations. We had a feature come out from ICESat 2. It doesn't specifically do with trees or land cover. It has to do with the mission and ice, but it's something I want to show you. And it's important enough to show you because the NASA Earth flagship account just shared it today on social media on their Facebook page, Instagram page, and X page. So I'm going to show you that way at the end before we adjourn for the day. So I'm going to show you that at the end before we leave today. So it's very cool, but it's called Chillin' with Paige and Foe. Those are our two ICESat 2 mission mascots. And I'm going to show you that also because, as you know, ICESat 2, that mission, the Ice Cloud and Land Elevation Satellite 2, is a huge part of our Trees Around the Globe student research campaign. All right, so a little bit of inspiration. Sorry, one of these quotes is very long, one is not, but I just thought these were interesting quotes to give us some inspiration for the webinar today. First one is from Marilyn Vos-Savant. You may have heard of her. In the United States, she is an American magazine columnist, and she is recorded to have the highest IQ in the world, or intelligence quotient, of 228. And I just like this little quote: to acquire knowledge, one must study, but to acquire wisdom, one must observe. Just thought that was great when we're especially talking about the GLOBE program. And then we have this famous author here who was also a professor of biochemistry at Boston University. This is Isaac Asimov. He was born in 1920, passed away in 1992. But he has this quote. He had some pretty wild, out of the world quotes. And if you ever read any of his books as science fiction, some of his science fiction writing was pretty out there as well, pretty wild stuff. I've read a lot of his books, some great stuff like Foundation Trilogy and all these things. So, but here's this quote, which I thought was interesting. I believe in evidence. I believe in observation, measurement, and reasoning confirmed by independent observers. I'll believe anything, no matter how wild and ridiculous, if there is evidence for it. The wilder and more ridiculous something is, however, the firmer and more solid the evidence will have to be. I thought that was interesting because, we're talking about observations here, right? We're really looking at observations when we're talking about GLOBE. But if we're doing the traditional GLOBE observations and measurements, or we're talking about the GLOBE observer, we're really talking about observation, okay? So with that said, I want to show you this because this video was just released back in, I believe it was the 25th of November. And, as part of the campaign, we have talked a lot about the moon trees. Okay, between Apollo 14 in the early 1970s, 1971, all the way through November 2022 and Artemis 1. This was a video that was just released. It's a really cool video. It shows basically the launch of Artemis 1 and then the planting of the Artemis moon tree at the Goddard Space Flight Center outside the Visitor Center recently. But it's a really cool video. As I said, it was just released, and I will put the link to this video a little later on in the chat so you can take a look at it. But what's cool about this is it goes through a really brief history of this Artemis mission and the moon trees, and then it talks a little bit about the planting and when I show this, because we've talked a lot about this moon tree, the history of the moon trees and the importance of it, of inspiring next generation of STEM. Um, but then also, this has been done. These plantings have been done all around, literally all around the United States. But then also, some of the early Apollo, Apollo 14 moon trees were planted in the United States, but there's also several in South America. But then there's also some second generation Apollo 14 moon trees that have made their way around the world. So I just want to show you this brief video before we get into some metrics, and then I pass it over to Dr. Erika Podest for her featured presentation. This is a very short video, as you can see. It's only about a minute and a half long, but this is an interesting video that was just released, just a couple weeks ago. Sorry if this sounds a little choppy. It might be a little low bandwidth stuff, but this is pretty cool.
And liftoff of Artemis 1. We rise together back to the moon and beyond.
I'm not used to talking about trees, like rocks. It's easier. Seeds represent the most optimistic of our species. Given our reliance on wood, from raw material for a home to a baseball bat, and now spacecraft, planting a seedling is an investment in our future. The tree may not bring you fruit, but it will bring future generations fruit. In 1962, President Kennedy said these words: "We meet an hour of change and challenge, in a decade of hope and fear, and an age of both knowledge and ignorance. The greater of our knowledge increases, the greater of our ignorance unfolds." Artemis 1 continued in the grand tradition of what Artemis 2 astronaut Victor Glover suggested during his visit to Goddard as vessels of humanity, that we take our culture with us into the cosmos. That we should choose to take seeds and plant them for future generations to enjoy, to remind us earthbound explorers that, despite the problems we face here, we remain connected to our future in space. I'm hopeful that all of our shared work on Artemis missions will bring similar fruit to future generations.
It's a nice inspirational message to start the webinar. And since since it's trees, we've talked about moon trees for, in this campaign for a while now. All right, so today I'm gonna start off with some housekeeping and some metrics, and then I will pass it over to, I'll do an update on the 2025 1-week tree height and land cover intensive observation period, which I have some numbers to share with you and some maps where we have the observations coming from. And then I will pass it over to Dr. Erika Podest for her Rhythm of the North, tracking the vegetation growing period from space. And then we will have some Q&A after that with Dr. Podest. And then I will pass it over to Professor Peter Nelson to wrap up and have some discussion and a presentation, discussing a little further, what Dr. Erika Podest discussed. And then we will have some discussion and Q&A after that, and then we will end then with that video that I promised, Chilling with Paige and Foe. So, okay, here's where our campaign folks are distributed across the world. We have some great numbers coming in. Draw your attention down to year 8, which we began on the 1st of October of this year. We have over 10,000 measurements between tree heights, land cover, and greening. So, super excited to see that. And for the total for the campaign so far, we're over 261,000 observations, closing in on 80,000 global sites. And that is as of about 2 hours ago when I did some metrics on the Globe website in the database. And you can see here we have a lot of campaign webinars. The 88 webinars are the monthly webinars. And then we have special ones that we did, with the campaign for different groups. Whether it be Globe Mission Mosquito or some of the Globe regional webinars like Globe Africa and LAC and all those groups that we did, the European Eurasia region as well. And then we have the blogs with over 375,000 views with the 82 blogs that we have that are part of the campaign. And you can find all those on our campaign website. We have a whole list of we have a whole bunch of links on the left side navigation screen on the campaign website, so you can check that out. All right, As you remember, we introduced last month's webinar, actually an email went out prior to the webinar that on the 21st of November, we began the 1-month tree height and land cover intensive observation period for the campaign. And we are looking to have, to have tree height and land cover observations for that period. And we are looking for observations globally, so both in the northern and southern hemisphere. Specifically, northern hemisphere looking for that change, looking for that green down. And these are just some of the pictures on the top here. Northern hemisphere, we can really see that green down, and then we see those, those luxurious green colors in the southern hemisphere. You can see here Argentina, Australia, Brazil, and Madagascar. So we're looking to see that. So what have we gotten so far? Okay, you may have seen an email go out from me last week with an update. This update is as of about an hour ago. And for tree height, we have 1,371 observations from 513 global locations. And you can see the map there that we're distributed pretty well across the world. And then land cover, 490 observations from 283 global locations. And I see out there in Oregon, Peter, it's, you guys are, got a lot of land cover observations out there, and we can see there's a lot going on there, kind of in the Midwest region as well in the United States. And, we got a lot of tree height and land cover observations in South America and Europe as well. So, that's just amazing stuff. So, thank you for the participation in that little circle you see down there on the bottom right. That is the digital badge that you can receive if you take tree height and land cover observations during this time. And this digital badge will be available, like this, but in a larger form and without that watermark that you see on the IOP website. This URL that you see at the bottom here under more about the IOP, you will see one, with a watermark on it with some text in the middle. You'll see that with that, where you can grab that digital badge and, keep it or add it to wherever you want to add it to. But it's just, thank you for taking these observations. So you can see we're getting some great observations. And, I love to see the tree height hit like 2,000 or 2,500. And I'd love to see land cover hit 1,000 observations. So, keeping our fingers crossed for that. But, thank you to all those, who have taken observations, especially those of you on the webinar right now. All right. Now, without further ado, I'm going to pass it over to one of our definite campaign favorites here, Dr. Erika Podest. She's a research scientist and NISAR Mission Community Engagement and Training Coordinator at the NASA Jet Propulsion Laboratory in California in the United States. And as you know, she has been with us for a long time with the Trees Around the Globe Student Research Campaign. She also was a major part of our SMAP campaign when we had it, and then also our El Nino and ENSO campaign when we ran that. So Erika has been with us for a long time with our Globe campaigns and all the work we've been doing. So, we hold her, of course, in high esteem with everything she's done, not just all her research and her, her STEM engagement, but everything that she's done with, celebrating everything that everyone's done, everything that everyone's done at Globe. But with all the research she's done and how she ties it into, what we're doing with the campaign and what's being done, with the Science at Globe and the observation. So without further ado, I'm going to pass it over to Dr. Erika Podest to talk about the rhythm of the North, tracking the vegetation growing period from space. And I will go ahead and stop sharing and pass it over to you.
Thank you very much, Brian. And thanks, everyone. It's a real pleasure to be here once again. Let me just share my screen. Okay. There you go. Can you see, everyone see my screen?
Looks good.
Great. All right. So what I thought I'd do today was talk a little bit about the vegetation growing period or growing season in the northern high latitudes. And I'll talk a little bit about the context, what is the importance of this vegetation in the northern high latitudes. So let's start with the carbon cycle, right? It's the cycle of carbon around our planet, and different parts of our planet absorb carbon in different ways, right? So you've got the oceans, they absorb carbon, they also release carbon. You've got land, you've got the soil, you've got the vegetation. So you've got different mechanisms that absorb and release carbon, and then the atmosphere, it accumulates in the atmosphere, right? And so what's happening over time is that carbon is being released faster than what is being absorbed, right? So there's always been like this equilibrium. We have the greenhouse gas effect on our planet. That's a natural phenomenon. And if it weren't for the greenhouse effect, our planet would be too cold to live, right? So this greenhouse effect means that we have a layer of gases that surround our atmosphere, and some of those gases are greenhouse gases, right? So these greenhouse gases, they absorb heat. The most common ones are CO2, methane, and what is happening is that we are increasing the amount of greenhouse gases that in our atmosphere, and so that blanket that surrounds our planet is getting thicker, right? So more heat is being trapped, and that is causing overall temperatures around the planet to increase. So this is a graph showing the increase in temperature since around the Industrial Revolution. But what you can see is that overall there's been a steady increase in global temperature on average, right? There are fluctuations from year to year, but on average, you can see the red line, there's been an increase, particularly since about starting in the 1970s, there's been a steeper increase in temperature, over around 1 degrees Celsius. However, there's been this increase, and we talk about the increase in temperature globally, but it's usually an average, right? There are areas of the world that are being more affected by this increase in temperature than other areas. And the areas that are being most affected are the northern high latitudes, the cryosphere primarily, or the extreme latitudes, right? So the extreme north and the extreme south. Today I'll talk primarily about the extreme north, the northern high latitudes, because you have a large coverage of vegetation in this area. So the impact is actually, and the implications and increase in temperature are quite significant in the northern high latitudes. But this is what we call the hyosphere, and the cryosphere, and when I talk about the northern high latitudes, it's about 45 degrees north. These are areas that have a strong seasonality. So you've got a very well-marked, summer, fall, winter, spring. So you have these seasons that are very well delineated or well marked. I'm in California. I do see 4 seasons here, but certainly not as strong and as in areas that are about 45 degrees north. So this is what we call the freeze and thaw cycle. And it has a lot of different implications, right? So not only for vegetation, but hydrology, ecosystem, meteorology. So this conceptual diagram shows the effects of freeze and thaw status and snow on, as I said, the meteorology, the hydrology, and ecosystem processes throughout the year, right? So in summer, you've got the low albedo. Albedo means reflectance because you don't really have any snow or much snow on the ground, so there's less reflectivity from the surface. In terms of hydrology, the snowpacks have melted. There's no active snow melt or runoff. And in terms of ecosystem, right, you've got plants that have usually wet soils or moist soils. And so they're growing. So it can be a very short period of time. It depends on the latitude. But these trees are growing during the growing season, which it can be 2 to 3 months, or even a little bit longer. It depends on, again, the latitude, right? And so you've got soil respiration, you've got decomposition. Then in the fall, you've got then the temperatures kind of freezing. You've got the snow starting to accumulate. You don't have any snow melt or runoff. And then you have the ecosystems, the vegetation kind of shutting down. They go into this hibernation state throughout the winter. And so during winter, basically, it's a dormant state. So there's really no or very little exchange of gases between the surface and the atmosphere. The vegetation is dormant. Soil respiration stops or is reduced to a minimum. There is still some gas exchanges. There is still some a little bit of release of methane from the soils even during the winter, but is not as significant as what is occurring during the other periods, right? And then in the spring, it's like a switch, and you've got snow melt, you've got wet soils, you've got runoff, you've got stream flow. The vegetation turns on, and you got the beginning of the basically of the vegetation growing season. So as mentioned, the northern high latitudes are really ground zero for global warming, for the increase in temperature that we're seeing around the planet. And so what we're seeing is that in Alaska, for example, temperatures have increased significantly more than the rest of the world. So in the Arctic, it's about 3 degrees Celsius warmer now than what it was in 1980. And this whole area is warming about 4 times faster than the rest of the world. So it's actually quite significant. And the reason for this is primarily, if you think of your refrigerator, in your freezer, and you put some ice cream in there is a big difference between a couple of degrees, right? So if you put ice cream in your freezer and it's 1 degrees Celsius versus -1 degree Celsius, it's going to make a big difference on that ice cream, right? It's going to make the difference between the ice cream being frozen versus it being thawed or very soft. And so these small differences in temperature, they might not be so significant, say, in the tropics, but when you go to the northern latitudes, the northern high latitudes, these differences of 1 degree, 2 degree make a huge or have a huge impact in these ecosystems. And one of them is the presence of snow, right? So one of the things that we're seeing with increasing temperature is snowpacks that are not as thick. And we're also seeing snowpacks that not only are not as thick, but they're melting faster, right? And so when they melt, they expose the surface. And so when the surface is exposed, which is dark, it absorbs more of the sun's energy. And so that increases warming, right? So there's the great albedo effect where these areas, when they're snow covered, cause a lot of reflectance of the sun's energy back into space. But when you have less of this reflective layer on the ground, then there is more absorption of the sun's energy, and it will cause even further heating. And so this not only happens on land, but also on ocean. In the ocean, we've got a lot of sea ice. Sea ice is being lost, right? So the white surface is being is disappearing, and it's exposing the dark surface of the ocean, which absorbs the sun's energy, causing the water to warm. And so there's a there's a lot of repercussions in this, and this is just another conceptual diagram to show the Earth's energy budget, how you've got the incoming solar radiation that is reflected by the atmosphere, by clouds, and from the Earth's surface. And so when you have that white surface removed, right, you remove this ability of the planet, the Earth, to reflect that energy back into space. And so future temperatures in Alaska are expected to increase even more. And this has obviously major implications, not only in terms of vegetation, but also in terms of what's happening in the soils. Because one thing is you've got the standing vegetation, but there's also something else called permanently frozen soils, and they hold a lot of carbon. So why should we care? These boreal biomes are the Earth's largest terrestrial carbon bank. And so when you compare the carbon in boreal forests versus tropical forests or temperate forests, there's a lot more carbon that's being held in these forests. I mean, primarily, part of it is you've got millions of acres of boreal forests in the northern high latitudes. And there's also, as I said, carbon that is stored in soils and permafrost, as well as wetlands. And just to put things into context, Canada stores about 208 billion tons of carbon, which is equivalent to approximately 26 years worth of the world's carbon emissions from fossil fuel burning. So I'll skip. I'll just briefly touch on this one, but this just delineates the boreal forests, and in Europe and Eurasia and Russia, it's referred to as the taiga. So you've got boreal and you've got tundra, and you've got a large number of wetlands here. You have permanently frozen soils as well. I'll touch on that. But just to give you an idea of the freeze-thaw cycles in these areas, I'm just going to show you some pictures. I've done a lot of work in Alaska, where we have sensors installed that measure the state of the soil and the vegetation. So we measure whether the soil is frozen or not, and we measure whether the vegetation is active or not, like if it's actually pumping xylem. And this is marked by the growing season, right? So during that period of time when the vegetation is growing, it's pumping xylem internally, right? So it's active. And then when it becomes dormant in the winter, it just stops. So we measure that with sensors that we install in the trees. So this is what it looks like kind of during that transition in the spring when the snow starts to melt. And so you've got this patchiness of snow and exposed surface, and then you've got, the rivers just you've got a lot of flow in the rivers. And of course, you've got wetlands. So the tundra is also a wetland, really a wetland ecosystem, because you've got all of this snow melting and you have surface water then accumulating. It accumulates in the surface, as you see here. And you have thousands of lakes up in the tundra. And since most of this area is underlain by permafrost, so the water just accumulates in the surface. Some of it evaporates during the summer, but it's just an accumulation of water. And this is what it looks like. So you've got forests, like thousands and thousands of hectares of forests. So how do we monitor this from space, right? So we use radar from space, and we use a number of different sensors to monitor the vegetation growing season period, right? So this is the period of time when the vegetation becomes photosynthetically active, that's in the spring, to when it becomes dormant in the fall. And this is really important because during this period of time, the vegetation grows and there is an uptake of CO2 by the vegetation, right? So it is actually significant enough so that you see the global concentration of CO2 decrease during this period of time because there's such a large uptake of CO2 by vegetation. And we can monitor this. This is just an example of using what's called radar. Radar is very sensitive to the state of water in the surface, whether the water is frozen or thawed. And this is a radar image in Fairbanks, Alaska, a time series radar image in Fairbanks, Alaska, near a place called Bonanza Creek. And in February, you can see that the image is darker as compared to May, June. And the reason for this is because the surface is frozen. And when it's frozen, there's less reflectivity of the signal. So radar systems are active systems. And so the signal, when it reaches the surface, it interacts with the surface, depending on the conditions of the surface, depending on what's there, but depending on the state of the water, again, whether it's frozen or thawed. So when there's liquid water in the surface, what we call dielectric, then there's greater reflectivity of the signal, as you can see here, for example, in 28th of June. And so that's how we can discern this beginning of the growing season, when you have this increase in your signal, what we call backscatter return. And we can then use satellite data or satellite radar data or microwave data to discern the beginning of the growing season in these latitudes. And this is an example that it's pretty old, but it does show the Pan-Arctic day of thaw. Let's see. Using a microwave sensor called a scatterometer. And you can do this from year to year to see how the growing season has been changing. So in this case, this is a microwave radiometer that data that was used to look at the onset of the growing season in the northern high latitudes. So what are the implications of a longer growing season? In terms of vegetation, you would think that it's a good thing to have a longer growing season because it is getting longer. We're seeing that the spring is occurring earlier, and the freeze up is occurring a little later. So that growing season period of vegetation is indeed getting longer, and it depends on the latitude, but in some places we're seeing 10 days earlier than 20 years ago, right? And so the implications are that the Arctic is greening. So there's expansion of shrubs, and there's also a shift in the carbon cycle. And you would think that this means that, okay, well, hey, we have a longer growing season, vegetation growing season. That means vegetation has more time to absorb CO2 from the atmosphere. So it should be a good thing. So it should be a larger carbon sink, right? However, that's in theory, right? In reality, it's much more complex because what we're seeing is that even though there's a longer growing season for vegetation, there is less water availability. The snowpacks are thinner, and there's less water in the surface for vegetation to grow. And so really kind of in the mid to late summer, it becomes very dry, soils are very dry, and the vegetation becomes water stressed, and basically it stops growing. Something else that we're seeing is that there are more and more of these extreme heat events. And so in these latitudes, vegetation is cold weather adapted. And so when you hit it with these extreme heat events for many days in a row, the vegetation will become stressed and it'll just stop growing. And so we're seeing those sorts of phenomena that we kind of have to balance between, its ability to take up CO2 and really to just become too stressed to continue doing that. Another thing that we're seeing is one thing is the vegetation, the other thing is the soils. And these soils, they're called permafrost soils, are soils that have been frozen for hundreds, thousands of years, and they contain a lot of organic material. And so what happens is the vegetation dies, that's organic material. It doesn't really have a chance to decompose because usually that period of where things are thawed is very short. And so that is going to freeze. And then, so that's organic material that's frozen and it's stayed frozen for a long time. In some places, this organic or permafrost soil can be a couple of centimeters to a couple of meters thick or even kilometers in some areas. And so the problem is that with increasing temperature, we're seeing that the soils are now thawing these faster than before. And so these permanently frozen soils are thawing. And this is actually of concern because that organic material that was stored in the soils is now being quickly released to the atmosphere. And so there are kind of two mechanisms there. One is through fires. So this is the tundra, actually. So this is a tundra, and we're seeing more and more fires, tundra fires. And so these fires really degrade the permafrost. And obviously, fire is just an instantaneous way of taking that carbon in the soil and in the vegetation and just releasing it immediately into the atmosphere. It's degrading the permafrost as well. And so this is a major concern because there are so many of these intense fires that are occurring. And also just the overall increase in temperature, as I mentioned, is just thawing out these permanently frozen soils. And so we're already seeing some of these effects in the soils where we have, you kind of see it in the trees, or they're referred to as like these drunken trees. They're just kind of laying over. It's affecting infrastructure, houses, pipelines, roads. So this is obviously a major concern, and especially in areas that are populated. And so the estimates suggest that permafrost, the carbon contained in the permafrost contains 2.5 times as much carbon as what's in the atmosphere. And so, the potential release of this in a relatively short time as things thaw is of great concern. So again, everything is in balance. So the vegetation is taking up CO2, but soils release, they store carbon, but they also release carbon. So at what point are they releasing more than what they're taking in? So that's really kind of what we're trying to, what we're studying and what these satellite data are helping us better understand, right? And so this next animation shows it shows two things. What you see in green over the continents, that's vegetation. That's vegetation greening. In the tropics, pretty much have green vegetation all the time. But in the northern high latitudes, again, that's going to be a seasonal thing. And what you're seeing in yellow, that is the amount of carbon dioxide in the atmosphere. And so what this shows is really our planet breathing. So as things green up in the northern high latitudes, there's a reduction in the global atmospheric CO2 concentrations. Yeah, obviously there's a lag, right? Because it greens and then you have this uptake. You see the uptake in global atmospheric CO2. But this just gives you an idea of the impact of vegetation in the northern high latitudes on global atmospheric CO2 concentrations. So yeah, usually when we talk about like the global atmospheric CO2 average, that's an average, but it's going to vary from place to place and from at different times of the year.
Erica, can I interrupt you a second? What's the time frame of this video?
Yeah, I believe it's down here. So
I just couldn't see it. I see the calendar. I just didn't see the years on there. Can't read the years.
let me see. Hold on, right. Brian.
I mean, you can tell us later. That's fine.
Yeah, I need to dig it up.
Okay.
I think this is like 2012, but or maybe
But
even more recent, but I'll have to dig it up.
but yeah, it definitely makes a statement. Yeah.
Yeah.
Yeah. Thank you.
And so another thing to note is that, I talked about the complexity in these ecosystems and in vegetation in the northern high latitudes. I talked about extreme heat events. I talked about less water in the surface. But one other thing I wanted to mention is that, with this longer growing season, and these stressors on the vegetation, you've got insect infestations, which are a big thing. It's becoming a big deal, like the bark beetle, for example. And usually, something like the bark beetle had one life cycle, right? Because it got too cold for that insect to survive. But now with conditions being more amenable and better suited for this insect, and longer, right? They're now living through two life cycles, right? So it's a double whammy for the vegetation. And so it really becomes weakened. So the vegetation weakens, it goes in through its dormant cycle, and then next spring, it kind of wakes up again, and it's already weak and it gets attacked again. So there's thousands of hectares of vegetation that is being affected, that is dying from these infestations. And obviously, whenever you don't you lose your forest, you lose that ability of the forest to take up carbon dioxide. So these are the sorts of complexities that I mentioned, right? So either directly through extreme heat events, and then indirectly through now, how those extreme heat events now is affecting the bark beetle life cycle, and 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 how that is now impacting the health of the vegetation and its ability to take up carbon. And so this is another slide I wanted to show you about, so the red is carbon, and how just things get transported around the planet. And, it just kind of shows you, primarily the red is carbon monoxide, but it shows you how what happens in one part of the planet is really affecting other parts of the planet. So we live in this unified world, where you think, oh well, that's Alaska, that's Canada, that's the northern high latitudes. I'm down here in California or in Central America, in South America, or South Africa, or whatever. But really, we live in a very interconnected world. So whatever happens in the Arctic does not stay in the Arctic. That's the bottom line. Okay. And so the last thing I wanted to touch on is I did want to highlight that there are several satellites that are being used to look at that freeze and thaw state of the land surface with microwave remote sensing. SMAP is one of them, and it has a freeze and thaw product. Um, and so this is just an example between two different dates on frozen land surface versus thawed land surface. So whatever is frozen is in blue, thawed is in red. And so you can see a distinct difference between just a couple of different days apart, right? April 1st and April 13th. So once you have this transition, it's actually pretty quickly. And as I said earlier, it's like a switch where things just turn on and there's this incredible growth for a couple of months and then things go dormant. There's another satellite that was recently launched into space. It's called NISAR. It's a radar sensor, and it with that sensor and with that data, you will have the capability to also discern the frozen and thawed state of the land surface. So that's looking at frozen and thawed, but there are other indicators. So there's like NDVI, where you're looking now at vegetation greenness and looking at the health of the vegetation as well. That can also provide an assessment of the growing season, at least for deciduous vegetation, and the health of the vegetation. All right, so with that, I reached the end of my presentation. Thank you very much, and I'm open to your questions.
All right. If anybody has any questions, pop them in the chat. There's none in the chat right now, but I have a couple, and there's a couple that some folks wrote me privately. So I have those. Let me open up my document here. One question is, you mentioned that you install sensors in the trees. Where in the trees do you install those sensors in like the boreal forest or in the taiga?
Yeah, so we install them usually in the trunk. It's easier to install in the trunk, around the trunk.
Okay.
And so the sensors, and they're installed in different types of trees. So we want to monitor the photosynthetic activity of different trees, whether they're evergreen or deciduous. So black spruce, white spruce, aspen.
And is there one like, are there different types of sensors? I'm assuming there's different types of sensors, and there's, you're trying to look at that photosynthetic activity, but I'm sure there's different levels of sensors out there that can do different things. Some more complex than others, more sophisticated. I'm assuming ones
Yeah.
that apparently have to be pretty robust to be in that type of environment as well.
Yeah, it does have to be pretty robust. Our system works with data loggers. So basically, we install the same type of sensor in all the trees.
Okay.
And at least for looking at xylem. And then that goes into a data logger that collects these measurements throughout the year. The data logger has a solar panel, and it also has a couple of car batteries there to keep it going when the sun angle is low. So in addition to measuring xylem, we're also measuring air temperature. We're measuring, we're looking at the presence of snow, and we are measuring soil temperature and soil moisture at different depths. So one of the things we want to understand is, it is a cycle. So if the soil is frozen, but the tree is thawed, right? So usually the tree thaws but the soil might still be frozen. Then the tree cannot draw water from the soil. So it's still photosynthetically inactive until the soil thaws and it can then start drawing water.
Excellent. Thank you. Another question was, so the wetlands, you showed a couple slides there. So the wetlands in the boreal forest are kind of like swamps during the melting season. That just kind of reminiscent of that, or is it something completely different?
No, so I wouldn't say they're swamps. You don't really get stuck in them. It's just like
Okay.
inundated vegetation. That's what it is.
And the last question that I received was, You have seen the effects of longer growing seasons in the boreal forest, and you mentioned that you have seen extreme heat events. What defines an extreme heat event in such high latitudes?
Yeah, that's a good question. So, I mean, even if temperatures go into like the 90s, mid 90s, that's considered an extreme heat event. And yeah, if they go for a day, a couple of days, then that does have, we're seeing that it does have an impact on the vegetation.
Thank you. Does anybody have any other questions? Feel free to put them in the chat or unmute, and we'll give you, a minute or so to do that. Feel free to, or raise your hand, and you can just go ahead and unmute if you like. If there's anybody who wants to ask something, maybe about their area. Or if you're shy, just pop it in the chat, and Dr. Podest can take a look at that in the chat. So we have a shy group today. So I had a couple people write me a message privately and ask me to ask it for them. I know when Peter does the Q&A, he gets a lot of those as well. All right, I don't see any more in there, but thank you so much, Dr. Podest, for the presentation today. That was super informative, and knowing about the boreal forest, I love the graphic that you put up because that's one of the, I think, the misconceptions that people um, have is that when we see that we have a longer growing season, we automatically assume that's always a good thing. But you brought that, with the water limitations at the end of the summer that can cause trees to become stressed. You have those longer periods of, the warmer climate, like you just mentioned, you have, longer periods of 90 degrees or more. That's, extremely detrimental to trees, in those areas. So, that's, I haven't heard it explained that way before. So thank you so much for that. We haven't heard it that way, presented that way, here, because like I said, that's a misconception that I think is pretty common, that, oh, longer growing season, that's good, more carbon dioxide can be pulled out of the atmosphere, which it can be, but it does have harmful effects on the trees as well when we have this this pretty rapid change like that. So,
Mhm.
but okay, yeah, all right, I don't see it. Oh, there's a one from Tracy in the chat. I'm interested in alpine, subalpine fog ecology. Do you ever look at that? Research would be helpful.
Yeah, that's an interesting point. No, I have not looked at that. Um, yeah, but that is really interesting, that horizontal moisture.
Yeah, it would be pretty neat to see what the effect of that is, in those locations.
Yeah, so Erica, I want to highlight that because I just had a graduate student working on this question of fog and sort of does it actually help protect from things like wildfires, specifically on the California coast. And I think one of the things that I want to sort of highlight about fog is the challenge of remote sensing it. Because of the timing of when this thing occurs, sometimes we don't have a satellite over at exactly that moment. And also we don't have a lot of reference data on the ground actually that helps us to know when there's fog there. So I realized as this student was doing their research that fog remote sensing is so challenging because of the time dynamic, the spatial analysis, the spatial scale of this, and sometimes some of the confounding factors that you have, many cloud layers above that. But fog is such a really interesting one that I think Globe Observer and our ground photos could actually really help with. And so, to me, that's sort of like, that first pitch of like, we need to define where fog is on the landscape. And then we can start looking at interactions between fog and what's there, right? But kind of just first figuring out and defining fog, I found actually is a really big challenge. Erica, can you talk a little bit about something like fog, which is like a ground cloud? But have you tried to remote sense and kind of like identify fog in your work over the years?
No, that I haven't. No, I've been primarily just focused on the terrestrial part, but I think it's super important, right, to bring in these components, different components together, right, to understand the fog and how that is impacting or changing the hydrology in the surface.
Yeah, and one of the things that came out that I know we have here in Oregon is there's an elevation line that
Mhm.
actually helps to define where fog tends to occur and where it doesn't. And since you have this nice picture of the coastal area right behind you, it just reminded me of how important that elevation value is when we talk about some of these dynamics. And so, I want to kind of highlight, all of these things are in what we're measuring from space. It just kind of takes somebody to dive in and look for that particular signal.
Mhm.
And so I just really want to kind of highlight that this fog one is one that any of us in the coastal communities were really curious about. And I was really surprised at how challenging that layer was to identify. And then again, by day. And so, Erica, you really highlighted some different ways of summarizing data as well, thinking about it in different scales, which I think is a really important thing as we, try to adapt and try to understand these big processes that you highlighted for us.
Yeah, and the one of the things that we're doing with satellite data is looking at the heterogeneity of the freeze and thaw process,
Mm.
right? So not everything thaws at the same time. I mean, there's an elevational gradient, as you mentioned,
Yeah.
and things at higher elevations tend to thaw later than things at lower elevations. Deciduous and evergreen trees, their thermal characteristics are different, right? So deciduous trees are naked; they don't have any leaves in the spring, while evergreen trees they have needles that are dark that absorb more of the sun's energy. So they tend to thaw a little earlier than, or yes, thaw and become photosynthetically active a little earlier than deciduous trees. And the same thing with north and south facing slopes. We see sometimes a 2 week difference between the thaw occurring in south facing slopes and north facing slopes, later in the north facing slopes, of course.
Yeah, and Erica, you really highlighted the complexity of this because, to me, that's where it gets really interesting. Where you can't just be thinking about that X variable latitude just going north. It's all going to be the same because a lot of us do have this elevation piece that also, plays into and might actually push us further north,
Mhm.
at least in terms of finding something similar to what we're experiencing. I know there's sort of a regular, for every 1,000 feet you go up, it's like traveling so far north. I don't have the number in my mind, so I'm not going to put it down here on video. But there is sort of, this piece where elevation is a really important part. And there's several other NASA projects that are focused on like this mountain rain or snow, or kind of this transition zone between where it's raining and where it snows, and how elevation plays a role in that, and how that's actually the important thing that we're seeing change. Because as you highlighted, Erica, if it's warming, we're getting more rain on these landscapes.
Mhm.
And when that occurs is something that all of us in the globe community can still record and report back. And to me, that's where these surface condition questions that are part of Globe Observer are really important insights into what you've presented here today. This, very simple question: is there snow on the ground? Yes or
Mhm.
no?
Mhm.
That gets into what you were highlighting. And then you'd have those photo evidence of sort of that patchiness of it, or is it the same, right? You also, one of the things that ends up getting recorded by people that they don't even realize is actually how reflective is that material? And sort of like, is it a cloudy day or is it really bright? And so, that really important piece of what you were highlighting in terms of reflectivity and not all snow is the same reflectivity, right? And then, I think one of the other really important sort of, pieces that we're highlighting with our surface condition question is whether there's standing water out there. And as you highlighted, that's really important when you start looking at radar signals or certain processes. And so, so don't be surprised out there if you find like there's snow on the ground and there's standing water. And there's actually leaves on the trees, right? Because one of the things that Erika, maybe you can clarify for all of us for this question of leaves on trees. How do you handle a pine tree or some of these trees that are evergreen, like you mentioned up in Alaska? Would you recommend for the globe community to be saying, yes, there's leaves on trees? Or would you actually be saying, no, there's not leaves on trees in that circumstance?
I think it's important to note whether there are leaves on trees. I mean, obviously in evergreen trees, there'll always be needles, right? But you've
Right,
got so many deciduous trees, and it's important to note that. Not only that, but the health of the tree. I mean, I've
right.
talked about the bark beetle, and so this, you could have evergreen or deciduous trees being impacted by this infestation. And
Mhm.
so noting that is also very important.
Yeah, yeah. So you're getting into those next questions that if people actually label their photos in Globe Observer, they would be telling us that composition of what type, what leaf type there is, whether it is that deciduous that is there only part of the time, and adds leaf area, later on in the season or at a different time, versus always having a green signal, always having needle leaf trees, for instance, being there on the landscape, always photosynthesizing, or, being green anyway. That evergreen is one of those misnomers. But this is something that we've seen in the data is people mistake that evergreen and they say no, that there isn't leaves on the trees.
Mm.
And because they're recognizing this deciduous component that's out there. And so Eric, I just kind of wanted to kind of like hone in on and help people recognize that, that question of whether there's leaves on the trees can be a really important one for us as scientists to try to, monitor things like that health, and be able to use that green signal to understand what the cycles that are happening there. But that's, one of those things, like I said, that I think I just love, as I think about all these trees that are going through winter dormancy or, getting ready to not photosynthesize as much, and versus places that tend to lose their deciduous leaves all the time. And that leaf area is really, kind of one of those magic words that you might see out there, which I'll say is part of like that up photo, whether it's coming from your cloud observation or your land cover observation. Again, is another way that you can gather some evidence about what that satellite might be seeing in that canopy leaf out, and when it does, right? So that's another place that I look for sort of that evidence of the leaf, whether it's greening or whether it's browning or some things like that. So, to me, all of these pieces, people are giving us some really interesting evidence if you start pulling it all together, and then hopefully, like what you said, combine it together with some weather data or some other data that might help you to understand that complexity that's out there. That's great, Erica. And so here, since you're still here, I want to take advantage of and share with you a little bit of the interesting cycle because of what we actually see in the data. Don't let the map fool you. We've got a lot more data being shown here, but we actually really do see this northern rhythm. And I'll say, a lot of that is because of the contributions of where our observations are coming from. So we actually have a little bit of a bias in our data. If we actually look at our latitude gradient here, we actually see most of our observations are coming in from the northern hemisphere, right? And so we can actually see that reflected in our data when we start looking at whether that answer to whether there's leaves on trees, right? This signal is clearly because of that northern hemisphere bias,
Mhm.
right? And if we could get more global representation, we might have a slightly different pattern to our data here. But I really like this because um, you know sometimes it makes sense that you don't have leaves on the trees in summer if you're at a certain elevation. They haven't leafed out yet, like you were highlighting, right? So even this the day of year is a fun little thing to think about as we think about what we might expect in our photos, right? And sort of like how green are these photos? Um, and how does that relate back up to that satellite data? But I want to highlight, one of the things too that we're missing in our data sets in terms of balance is people tend to go out and only do our observations when there's not snow on the ground. And that's partly because again we tend to get most of our observations during the summer months. We don't have as many coming in during the winter. And so we actually have this seasonal bias to our data as well, which makes it hard to really pick out this, the snow or an ice and that seasonal shift that you were talking about, Erica. But every once in a while, you sort of see it kind of come in where we actually go from October and we start getting an increase of our snow observations until February, and then they start kind of going away, right? Kind of following that melting season that you really highlighted for us earlier with some of those videos. So, to me, I get excited when I start seeing a little bit of the same patterns that you see in the satellite data
Mhm.
in our globe data, in
Oh,
in
wow.
some of our globe observer data. And if we could just get more and more of this coming in, right? Like you can really see how this can help you with some
Right.
of these challenging questions that we were highlighting earlier, like dealing with clouds or dealing with, some of the volume that you get with snow that
Mhm.
currently is another big one of our challenges, right? So I wanted to kind of dig in with that with you because it really, to me, it shows the value that our community is providing, but there's some nuances that we want to be thinking about. Like we don't, represent the south of the equator very well. So some of the
Mhm.
questions, globally, we can't really look at as much, right? But back to what Brian has highlighted, here's kind of like just our last month of data, and here we're coming in with quite a bit of focus with 2,500 locations that we've been able to do. So I just kind of want to follow up and say, like, keep doing this, keep contributing, help us really get this transition because I know where I'm located in the western part of the United States. We don't have our snow yet. We're still waiting for it. When we keep transitioning from rain and snow and kind of going back and forth, and so Erica, we're right in that area where it can change on a daily basis like that.
Mhm.
And so I hope that people will be watching some of these events that are happening right now and contribute to this giant data set that we're putting in here, which I'm pretty excited about, even with some of the filtering that I already see that we're going to have to talk about. But,
Yeah.
Erica, thank you so much for highlighting the satellite data that people can see with all of these. And I think it really complements what we are observing in our local place. So that's what I wanted to highlight today is a little bit of encouragement for people to dive into the data and see what ends up happening when you pair up with somebody who's not near you, right? You might be able to pick up some of these signals that otherwise you're just sitting in the same place, experiencing the same freeze up, freeze down. All the numbers are the same. But if you reach out to other people in the globe community, you can get that contrast and I think highlight or make measurements that really complement what you've shown us today, Erika, at that global scale of things.
Yeah, no, that's great. I need to jump off, but yeah, I just wanted to say that it's super exciting to see, the data set that has been collected through Globe. And Peter, you're absolutely right. I think im there are super important observations to be done during the transitional periods,
Yeah.
right? Because that's when it becomes more difficult with the satellite data to really assess the conditions on the ground because there's so much heterogeneity. So observations on whether, leaves are on or off, or whether there's snow on the ground, all of that stuff is really important. So thank you, everyone, all the participants, and thank you, Brian and Peter. And I hope to be back and then see more of the globe measurements and see how we can integrate them with the satellite data.
Thank you
Thank
so
you so
much.
much, Erika.
Yeah, thank you for the great presentation and always being here for us in Globe. Thank you so much.
Sure thing. Thank you. Bye-bye, everyone.
Bye. All right. Anything else, Peter?
So yeah, since I have the floor here a little bit, what I wanted we jumped off and we're talking about the ground photos, right? And I think this is again one of these sort of great things that you can actually just even see at this global scale here between like the tree down in Brazil versus the lack of leaves up here in Alaska, where we were just kind of highlighting. And so, so I really do encourage all of us to go through and use this database to look at that seasonality, like Dr. Podest was really highlighting right there. Of course, this one's not showing up because it was from yesterday, but that's the way the world works, right? And but one of the things that I want to really stress, because this kind of showed me this, is that we really want you to be paying attention to your latitude and longitude. As you saw Dr. Podest really highlight there, this is very important measurement. If you are in a certain place, we can expect certain patterns to be happening or certain experiences to be happening because we are measuring those things from space. If your data ends up in the wrong location, it makes it really hard for us to compare it to what we're measuring from space and to get that corroboration that we're really after. And so I hate to kind of pull out, but I'm going to. This is why it's really important to check your data. Is here we actually have a location that showed up in Russia. And so, to me, having this reference data behind us of country boundaries is one of those ways that I am looking to double check to see, is this a value, is this a useful image in this location? And when I actually go in and look at the measurement itself, I can get a little bit more insight into maybe why it showed up in a suspect place. Place that I'm just not certain that it really is. And I get some notes sometimes that tells me it's a trading or it's something like that might be a reason why I might want to disregard or do something different with that data. Again, this is a really important step before we do a comparison to what Dr. Podest was showing us earlier. One of the things that is really useful when you're using Globe Observer is we have this location method and accuracy that, again, is one of these flags that us researchers use all the time. It's one reason why Dr. Podest has that the instrumentation setup that she was showing us, because she really wants to make sure she's in the right location. If you see something like this where there's a very large number, as a researcher, that brings up questions about where we're located in the world. So please, 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 please pay attention to where you are in the world. Use the Globe GPS protocol to make sure that you are locating yourself well. Because again, that to me is just kind of one of those pieces that is like, oh wait, we're in sort of a country of globe that isn't as active. Right. The other thing I wanted to highlight that I just happened to see as we were in here is, oh my gosh, I'm starting to see some things out in the middle of the ocean, which also is a little bit of a flag. And so when you are putting your data in, again, we can see this is coming from somebody in Brazil. So I would expect that to be on land, or if it's not on land, to have photos of water, right? Um, and so I'm going to have to wait for that one, to see the photos. But this to me was one of those where we're going to have to go in and look at the location of this data. Because it's out in the middle of the ocean. That's just kind of one of these big flags for all of us. Most satellites turn off and don't actually make measurements out there. Some of them do. But that's one of those things that when you go into the Globe database, what I want to show you is if we look at the satellite data, we can actually see a lot of the things that Dr. Podest was highlighting. So make sure that you turn that on and look at it, because one of the things that you're getting is a cloud-free image that is actually kind of showing you the greenness. How green is this location? And that's averaged over the whole year, right? And I want to highlight that because that's one of those things that we're looking for is, when we're looking at this vegetation pattern, we're looking for green, both in our ground photos as well as what's coming from space. So I'm going to end here with highlighting that you can again, tap into the satellite data that's made available by NASA for your measurement whenever you made your globe measurement. Now, again, if it's out in the middle of the ocean or not in the right location, this comparison is going to become very obvious. And the reference of the satellite data and the map behind it will help you to figure this out. Right. But this is a really interesting because, again, you can see what is happening near the equator. And then as we move further north, we can start to see, some of the winter patterns that Dr. Podest was highlighting. So again, making a determination between snow and clouds is one of these big things that we're doing. That the ground photos that are coming in through our IOP are exactly what we want, what we need, and we need to be able to provide those to people like Dr. Podest to be able to see these big rhythms that are happening across the globe. So with that, Brian, I'm going to hand it back to you to wrap us up for our December webinar, and I think it's really interesting to be thinking about that tree question of leaf type, and are there leaves on the tree still, or are they not? Because I've even had the experience where I've seen leaves go brown, but they never actually get blown off the tree.
Yeah.
Which was just again one of these very interesting patterns that I wasn't expecting until I saw photos.
Yeah, it's interesting that you say that because I was having a conversation with a couple that walk around our neighborhood, and in our yard we have all these trees that drop their leaves, and we just did a yard clearing of all the leaves, like so many trees in our yard. And there's one tree where we have this huge lower branch that I swear all the leaves are brown, but not a single leaf has fallen off of this large branch.
Right.
The
Yeah,
craziest thing. And the other
that
thing,
leaf longevity
yeah,
is really that keyword that we're looking for right there. And to me that's been I've been surprised at how you can see wind interaction, you can see some of that weather reflected in the pictures that we're getting here through this IOP and through some of these measurements.
Yeah, and the other thing that you and Erica were talking about is that question that comes up often is, are those pine needles considered leaves? And that's been like, racking my brain forever, and when you Google it and things like that, you see that yes, pine needles are considered leaves,
Yeah,
so, are the leaves still on the trees? And if you're in an area where there's, you're taking where there's pines and the needles are there, yes, the leaves are on the trees. So it's, I've been guilty of, in the middle of winter, being in an area where there may be one pine tree and the rest are leafless deciduous trees. There, I've gone in and said, nope, no leaves on the trees. I've been guilty of that, in the past. And
yeah,
that's such a tricky situation. People think of leaves as just being on deciduous trees, and that's a tough one, right? So,
it
um,
is.
so yeah, I mean, and
These are, I mean, again, Brian, this is kind of why one line of evidence, one line of data is not the end all be all with these
right,
patterns, right?
yeah,
And Dr. Podest really did a great job of highlighting all
yeah,
the different ways that we go to understand what's happening below the ground in the pedosphere, as well as what's happening, above ground and all the way up into the atmosphere like that. And to me, that's the take home point is like every day is unique and different. It's
yeah,
not the same as it was in the past. And so, to me, that's the encouragement that gets me out every day to make my observations. And I hope other people will find that same sort of reason in these cycles, in these rhythms that you can really start seeing with the unique measurements of remote sensing like this. And remote sensing in Globe Observer and you're off your phone or all the way up in space, like what we got to see today.
and so keep taking those observations, right? Keep taking them.
That's right, exactly. Like I said, every day is different, and you never know when you found the pattern that was revealed in the satellite data.
All right. So the last thing I'm going to show, and I saw our colleague Valerie Casasanto was on, but she had to go. She is the outreach and communication coordinator for the ICET-2 mission at the Goddard Space Flight Center. So I will go and introduce it. I'm the education lead for the ICET-2 mission at NASA. But I'm going to show you this because this was recently released, actually just a few days ago, and it was just shared on the NASA Earth flagship accounts, social media pages on Facebook, X, and Instagram. And this is called Chillin' with Page and Foe Ice Sheets. And even though this is specifically tree related, it does get up into that area, where we are kind of talking about today, up into that high latitudes. We're talking about the ice sheet. So there's two ice sheets on the planet, right? We have Greenland and we have Antarctica. So, as an Earth system, the complex Earth system we have, these ice sheets, even though they're in that northern latitude, we're in that, the southern latitudes, they do whatever's happening on those ice sheets, they affect the entire planet, right? So, but I wanted to share this with you because this is really cool because with the ICET-2 mission, we've had a relationship with the Savannah College of Art and Design, or SCAD, and the students there in a program called SCAD Pro. And this is in Savannah, Georgia, in the United States. So this program is filled with amazing students who work on visualization, production, art, art and technology, design, really, really cool things. And they've created a lot of stuff with our collaboration with the ICET-2 mission. And this is a video reel that came out recently with our two, Paige the Penguin and Foe the Photon, our two mascots with the ICET-2 mission. As you can see here, all you're seeing here, this is kind of a teaser. You're seeing, it's hard to see, but this is what you're seeing is ice, and you're seeing these two virtual reality goggles here. But this is a collaboration between ICET-2 and SCAD. You can see there's a whole line of credits here for folks who have worked on this. But I'm going to play this for you. It's very short, but the featured speaker in this is, you'll see here, Dr. Dennis Felixson. He is a deputy project scientist with ICET-2, and he's going to be talking about ice sheets, and you're going to be brought along for the ride with Page and Foe. So this is called Chillin' with Page and Foe. And then once this is over, I'm going to pop back into the main room, and I'm going to, pop in here the link to the video that you can check it out. And it's also going to be on the webinar page too. I'm going to share this once I get the webinar up. after this. Oh, and before I do this, I want to mention that we will be having a January 2026 webinar. We just don't have that date finalized yet. Our campaign team will be meeting on Monday to discuss that, and we will come up with a date, and then an email will be sent out early next week with that information. So stay tuned for that. So let me go ahead and play this. This is a lot of fun. So here we go. Let's check it out.
Begin simulation. Hey, Paige and Bo. It looks like you found the edge of an ice sheet where it breaks off into the ocean. Ice sheets are formed on land in really, really cold places like Antarctica and Greenland as snowfall builds up over thousands and thousands of years. ISAT-2 measures the height of those ice sheets so we can tell where they're growing and where they're shrinking and by how much. The biggest changes we see are in areas like the one you found, where the ice sheet meets the ocean. There, the warmer ocean water causes the ice sheet to break off and melt into the water itself. With ISAT-2, we found that water is melting from the Greenland and Antarctic ice sheets at a rate that could fill 4 Olympic-sized swimming pools every second. Over the last 20 years, this has raised global sea level by about half an inch.
So that was a cool, quick little short that we created just to get that information out there about ice sheets and what we're seeing with the data from ISAT-2. So let me pop that link here. I already put the data in here, but I didn't hit submit. There we go. So just wanted to thank everyone for joining the December webinar. Stay tuned for an update for the January 2026 webinar. Hope everyone has a great December. And a great rest of the year. And we will see you all in the beginning of the new year. So thank you, everyone. And stay tuned for the information coming out about the recording and when it'll be online. Just got to wait for Zoom to get me the process video. Then I have to do some editing before I get it up on the website. So thank you, everyone, for being here, and take care.